Okay. Last time, right? Yesterday we started to discuss Poisson processes. Let me again remind you the definition of a Poisson process and then continue doing a couple of interesting examples about it. Okay. So how did we define Poisson process last time? So a continuous time stochastic process X, okay, is called a Poisson process with a non-negative deterministic intensity process lambda, right? Lambda t of t. If this process X satisfies two important properties or the conditions. The first one says that process X must have independent increments. Okay, and the second one was describing the probability distribution of the increments of this process. Namely, for example, for every S and T, okay, the random variable xt minus xs, right, the change in the value of the process over the interval from S to T, has Poisson distribution with mean given by the integral of the intensity process from the beginning of the the integral of the intensity process over this interval. Let's say like that, right? So we have interval from S to T, right? Then the increment of this process over this interval, right, has Poisson distribution with mean which is calculated, which is found by integrating this, let's say, the intensity process lambda over this interval. So this area under intensity curve over this interval from S to T will give us the mean, right? And we said if lambda u, the intensity remains constant for some given constant number lambda, positive lambda, right, then that mean of the Poisson distribution is always constant lambda times the length of the interval t minus s, right? And then xt minus xs has the same distribution as any other increment over any interval with the same length t minus s, right? And has distribution with Poisson distribution with mean lambda times the length of the interval, right? Okay, right? Okay, let's look at the following exercise. So in this case, the special name for this, for the same process X is what? X is called a homogeneous Poisson process. Okay, and the reason is that xt minus xs has the same distribution as xt minus s, right? Well, it is common actually to assume that at time 0 process x starts from 0, but that is really not necessarily the case in many applications that we may consider. Therefore, I don't insist on that. Okay, so these two random variables have the same distribution. Have the same distributions. Okay, so let us look at exercise 1.9 in your textbook. Okay, this is on page 275. Okay, and in this case we are again given a Poisson process X. We know that it is a homogeneous Poisson process. Okay, with rate lambda. Okay. Okay, and we would like to calculate, and let's also assume in this case that at time 0 the process starts from 0. Okay. In part A, we would like to calculate the expected value of x2, right? So last time we said X is a typical model, a Poisson process is a typical model for arrival, is an example of an arrival process, right? It counts number of, you may think that X actually counts number of arrivals over any given interval, time interval. So if we have such a system, let's say X counts the number of arrivals to a facility, then xt is like what? The number of arrivals to this facility until time 2. Right? And in this case we are interested in expected number of arrivals until time 2. Right? We may just ask, for example, what is the expected number of students who are going to come in class in the next 15 minutes? Right? If that is really following a Poisson process, right, then we can say something about it in more explicit terms. Other things that we would like to calculate, okay, we would like to calculate the expected value of the square of x1, okay, and also expected value of the product of x1 and x2. Okay. Okay. So let us start with the first one. So now, since we know X is a Poisson process, by the second property, that the X2 must have Poisson distribution, right? So we know that the X2 has Poisson distribution with mean 2 times the rate of the process, right? 2 times lambda, and therefore, and we know that the mean of a Poisson random variable is its rate, right? Or, well, actually we should say that this is the mean of this Poisson distribution. So the answer for this question comes right away, right? We know what this is. And how do you calculate this one? You should just remember how we calculate variance first, right? In general, okay? If y has second moment, then we know that the variance of random variable y is given by the expected value of the square of random variable minus the square of its expected value. And if you are interested in this, which is the case in our problem, and if you also know the variance and the mean of this random variable already, then we can use this expression to calculate the expected, well, the second moment of this random variable, or the expected value of the square of random variable, right? So if we just replace, now we know that x1 has Poisson distribution with mean lambda, right? And Poisson distribution has all the moments, and in particular its variance and its mean are the same and equals lambda, right? And then if we just replace y with x1, then we get what? We can find this by first calculating the variance of this random variable and then adding to that the square of its mean. As I said, this is, in this case, okay, since x1 has Poisson distribution with mean 1 times lambda, right? So this is now lambda, and inside the square you have lambda as well, so you have lambda squared. Okay? And so in the first two parts, we use the random variables we are working with have Poisson distribution. Here, again, they are not independent, right? Because x2 counts number of arrivals until time 2, into which also the number of arrivals until time 1 contributes. Right? So we know that this is part of this count here, so they are not independent. Therefore, this expectation is not the product of expectation. We cannot do something like anything like that, so we have to be careful, right? But then we can again use, right, stationary independent increments property of our Poisson process X, right, to write the product first of all as what? So x2 consists of two parts, right? Number of arrivals until time 1, and then additional number of additional arrivals from time 1 to time 2. Right? We can do that. I just split the contributions to this count, right? From the interval up to time 1 and the time interval between from 1 to 2, right? And then if we just expand this, then we have x1 squared plus x1 times x2 minus x1, right? And this random variable, these two random variables are independent now, because both of them give us what? The increments, the change in the process x, one over the interval from 0 to 1, and the other over the interval from 1 to 2. Since intervals are disjoint, and since Poisson distribution, Poisson process has independent increment property, so they are again independent. So if we take expected value now, right? Then I have to calculate, I can calculate at least this one by first calculating the expected value of the square of x1, and then expected value of this product, right? And what do I get from here? I can use the same trick here. So this is what? This is the variance of x1 plus the square of the expected value of x1. Okay, that takes care of this first part. And the second one is going to be what? Since they are independent, the expected value of the product is the product of expected values. Let us write it here. So expected value of x1 times the expected value of x2 minus x1. But we know what? X is a homogeneous Poisson process. So x2 minus x1 now has the same distribution as x1. Right? So I will have then expected value of x1 times expected value of x1, namely the square of expected value of x1. right? Then we can just combine all, plug in the values. Now x1 has Poisson distribution with mean lambda times 1. Therefore this is lambda. Variance and the mean are the same for the Poisson, homogeneous Poisson, Poisson distribution. Okay, and here then I have mean squared, lambda squared plus, okay, I have the same, do I'm not making any mistakes, right? And that means I have 2 times lambda squared, right? Do we have any questions right now? Okay, let us look at another example, another problem. So this is problem 110 from your textbook. I guess it is on page 277. Okay. Okay. Now the question reads like this. The customers arrive at the facility at random according to a Poisson process with rate lambda. Okay, so we again have a homogeneous Poisson process with intensity lambda times t for some fixed lambda. And there is a waiting time cost C per customer per unit time. So here people come there waiting for service. For each unit time, each customer waits over there, it costs us $C. It's like probably an inconvenience or impatience cost, let's say. Somehow they quantified this particular cost. The customers gather at the facility and are processed or dispatched in groups at fixed times t, 2 times t, 3 times t, and so on and so forth. So again, we may think like actually we have maybe we are at the bus station and the buses come there and depart exactly at time t. The first bus departs and then the next bus will come there, wait until time 2 times t, and then departs, right? And each bus just will wait there to collect passengers. But any passenger who comes between any 2 departure times will just sit and wait inside the bus, right? If they wait too long, then they will be impatient, and the cost is going to be like around C for each time unit per customer. Okay, and there is also a dispatch cost of K. You may just think this K as like actually the cost for one trip for one of these buses. Okay, so what could be a natural question in such a setup? So we fix that T, right? If T is too long, then people get actually more impatient. Maybe they just will not want to use that service at all because they will not be able to go wherever they want unless they are willing to wait a lot longer for the bus to depart every time they arrive to there, right? So if the departure times are getting longer and longer, right? That's not good. But if T is short, then you will have actually more frequent bus trips, right? And then you are going to be paying actually a lot for the gas and all other things like that, right? Because you are actually running buses more often than you used to do that. Now the question is then going to be what? What is the optimal T? It shouldn't be too large, it shouldn't be too small. You should choose T in such a way that the impatience cost to customers and the dispatch cost together, when you sum them up, is going to be minimized, right? So both of them will depend on T, right? If T is large, the impatience cost is going to grow, but the dispatch cost is going to get smaller per unit time, right? So you can save from dispatch cost by actually making T larger, but then of course the other trade-off just goes up, namely the impatience costs will actually increase. The other alternative is just to let T actually choose, you can choose T smaller, right? If you choose T smaller, okay, waiting costs are going to be smaller, but then the dispatch cost is going to be large, right? So there is a trade-off between waiting cost and dispatch cost. So we will just shift t back and forth till we find actually an optimal trade-off between these two cost items. Okay? So that's the problem. That's the problem. So we would like to know the expected total waiting and dispatch cost per unit time during the first cycle, or actually during any typical cycle. Cycle being what? A bus stops at the bus station, everybody gets on, and next time, at time t, it is going to depart. So that's one cycle for us. It just repeats itself over time. Right? If we find actually, the first question is first of all, we would like to find the expected total waiting and dispatch cost per time unit in a typical cycle. And in the second part, we would like to choose t that will minimize whatever that cost is going to be. Right? So we will first quantify the waiting cost in terms of t, and then we will have a function that we can minimize with respect to t to find the best that will minimize the overall cost. Right? Is it clear? Is the problem clear? Okay, so we have customers, right, arriving to a facility according to a Poisson process, right, with rate lambda, or equivalent with intensity lambda times t time. Okay, and there is a waiting cost c, right? So this is waiting cost per customer per time unit. Okay, it is given. Customers gather at the facility and then are processed or dispatched in groups at fixed times, like T, 2T, 3T, and so on and so forth, right? So, okay, these are, this is just a summary of the question, right? Customers dispatched, right, in groups at fixed times T, 2T, 3T, and so on and so forth. Okay? So we can draw a picture and visualize what is going on. Let's put on the horizontal axis time, T. Right? On the vertical axis, we can put number of customers waiting in the facility, number of customers waiting in the facility, right? That's enough. So there are these dispatch times at time capital T, at time 2 times T, and 3 times T, and so on and so forth. Right? So right after these times, we know that the number of customers, there will be no customers waiting, the number of customers waiting will actually drop to 0. And then it is going to start increasing with the arrival each time a new customer arrives. Right? For example, if the first customer before time t arrives sometime here, the number of customers in the facility will jump by 1. Okay? And it will stay like that for a while. And when another customer arrives, again the process jumps. It stays there for a while, and then it again jumps when another customer comes. And let's say in this case there are 3 customers at the time the first bus is dispatched. Right? We just remove them from. In a sense, we serve these 3 customers, so they leave the facility, and then the number of customers waiting in the system drops to 0. Right? And at some other time, some time later, the first customer shows up, right, in this second cycle, and then we will have perhaps a second customer before the second bus is dispatched, right? And then we will have a process like this. Okay? It starts at 0, jumps to 1, and then 2. Okay? And you may have a similar picture for this one as well. The first customer comes, maybe nobody will show up by the in the remaining part of the cycle, and then there will be only one customer served in this third cycle. And each one of these is a cycle for us, right? So we have 3 cycles then here, right, in the picture. It goes like this. And we would like to calculate first, or we should also mention that we have a dispatch cost K. Okay, so this is the dispatch cost. Okay. So this is a fixed cost that we pay for each dispatch. It is constant. We know beforehand what it is. And in part A, we would like to calculate the expected total waiting and dispatch cost per time unit in a typical cycle. Now, statistically, each one of these cycles are identical, right? Because as soon as one of the buses leave, right, starting from that point on, the arrival process is still Poisson. Right? People arrive according to Poisson process. The system starts from state 0, and there is again only t units of time until the next bus leaves. Right? So number of people who are going to show up and the times when they are going to show up during a cycle is always going to be the same, statistically be the same, right, across the cycle. So statistically, each one of these cycles are identical. Therefore, if we just actually analyze one of the cycles, that also gives actually, that's also the way we see, that analysis will apply to any one of these cycles. Okay? Therefore, we are interested in expected total waiting and dispatch cost per time unit in a typical cycle, or you may just say the first cycle. There's no difference. And then, of course, this cost, expected cost, will depend on t. And in part 2, we would like to find the best t, in the sense that it minimizes the cost per time unit, right? In part I. Okay. The find optimal t. Okay. Optimal t, which will minimize. Right? Optimal in the sense that it is going to minimize the expected total, the expected total waiting and dispatch cost. Okay. So, how can I find, well, okay. In part A, before we calculate the cost per unit time, let us calculate the total cost in a typical cycle. And obviously, once we find the total cost, then we are going to divide it by the length of the cycle, which is capital T, to find the cost per time unit. Right? So what is the total cost? Total dispatch cost is also known, right? It is K, because during a cycle, well, there is only one dispatch that is performed, right, at the end of that cycle. So we know that total dispatch cost equals K, so we can add it later. So the thing that we have to figure out is the expected total waiting cost of customers in a typical cycle, right? How can I find that? Well, we can just argue like this. So for every customer, well, I should say that for every, or maybe I should even refer to the state. Did we introduce that? Not yet. So this cost will definitely depend on how many customers customers waiting in the system at the moment, at any given moment, right? So let's define xt, or denote by xt the number of customers waiting, right, at time t. Okay, waiting in the system at time t. At time t. Okay. Right. So until, okay, then we know that if you look at the process xt until the first dispatch time, let's say, right, this is the same as the number of customers entering the system, because each customer that enters the system before the next dispatch time is going to just wait. He has to wait, right? So the number of customers waiting in the system will increase by 1 as soon as a customer arrives. And since we know that arrivals of customers follow a Poisson process, at least up to time t, this is what? A Poisson process. A Poisson process over a fixed interval. So this is a Poisson process with rate lambda. Okay, we know that. Now, each one of these customers, right? So at time t, you have xt number of customers in the system, right? Now, each one of these customers will have to wait for at least another infinitesimal amount of time, right, before dispatch happens, right? For whatever the unit time is going to be for each one of them, and they all that waiting time is going to cost us c, right? C unit per time unit per customer, right? So we can just write it carefully here. For each of xt customers waiting at time t, before this dispatch time, capital T, right? We incur a waiting cost, right? We incur waiting cost C times, right, dt over the interval, time interval, from t to t plus delta t. Okay? So the guy is over there. dt is like what? The smallest, whatever the time unit that we are concerned here. Over that small interval, since t is strictly less than t, there is always such a small interval, right? Over that small interval, each one of them is still waiting in the system, and for each one of these customers and for each time unit that is passing before dispatch takes place, we pay c, right? The length of the interval is dt, so c dt is the cost per customer. At time t, I have how many customers? xt customers, right? So then we can find, by this reasoning, total waiting cost, right, at time t over the same interval, time interval from t to t plus delta t, or dt, equals xt times this cost, right? Because there are so many customers, and we multiply it with the number of customers present in the system at time t. Okay? And we can use this, so there are, what? We have to calculate total waiting cost over the entire cycle. And a cycle consists of such intervals, right? From 0 to t, we will just sum over those integrals, those intervals. And the way we do that is just to take the integral of this thing, right? So this is the cost over this interval. And I have many of them from 0 to t, right? I have t here. So this is dt. So over this small interval, that's the cost. I have to just calculate the cost over each like a small interval like this, and then sum all the associated costs. And we find that thing as what? The integral of this instantaneous cost, waiting cost, over time intervals from 0 to t. So total waiting cost per cycle, right? Or maybe I should just describe the interval. Cost over the interval from 0 to t, right, equals what? At time t, I knew that the cost was this. Now I have to integrate, sum all these costs over the entire interval. So it's just the integral. Right? Do we have any questions about this? Are we comfortable with this? Huh? Then if you want to calculate the expected cost, or maybe I should not touch that yet. So then now total waiting and dispatch cost over the interval from 0 to t now is given by, well, we know now, okay, that this is the total waiting cost, and we only have to add the dispatch cost to find the total cost, right? And the expected total cost, now we can write that right away here. So expected total waiting and dispatch cost is then given by the expectation of this. Okay? And expected total waiting cost per time unit, total waiting and dispatch cost in a typical cycle per time unit, okay, is given by, is found by dividing this by t, right? So this is 1 over capital T, the length of the cycle, times the expected value of the integral c times xt dt, right, plus k. Okay. Now we can get even more explicit result now, right? We said integration is nothing but a summation, and we know that we can interchange the summation and expectation, especially if this is non-negative. And then when we do that, right, we get what? C times expected value of xt integrated with respect to t. Okay, there is k outside. We should not forget that. Right, we have that. Right? And what is this? What is the expected value of xt? That is what? Expected number of customers waiting in the system. How do we find that? Lambda t, because xt has Poisson distribution with mean given by the rate of the process, Poisson process, which is lambda times time t. Right? So this is lambda times t. Okay. And therefore that is 1 over t, right? C times lambda goes out, times the integral from 0 to t, it is just t times dt plus k. And this is what? T squared over 2. So we have c times lambda divided by 2 times t squared plus k. And then we can divide by k by t if you like. So we will have lambda c times lambda over 2 times t plus k over t. So that's the expected total waiting and dispatch cost in a typical cycle per time unit. Okay? So that's the answer for the first part. And you can see we can plot this cost and its components. So let's say this is the cycle length t, right? And here let us put the cost, expected cost of different kinds that you're interested in. Well, expected cost per time unit, in fact, right? Per time unit. Because we divide it by this cycle length. So the first part is what? The expected waiting cost per time unit. And it is what? It is linear. It grows like this, with this slope c times lambda over 2. And this is what? This is the dispatch cost per time unit, which is k times 1 over capital T, and it is something like this. So the expected waiting cost per time unit increases, right, with cycle length, which is not surprising. We already discussed that, right? So this is expected total waiting cost per time unit. And this is what? This is dispatch cost per time unit. And the sum gives us the expected total cost per time unit, which is going to have a form like this. Ooh, that's too much. So it should converge to this one, right? Because this is diagonal. Okay, so this is the total cost per time unit. And we would like to find in the second part, we would like to find cycle length that will minimize this one. And obviously there is one, right? We in fact see that it is given by the intersection of these two curves, right? But without really worrying too much about that, if we just take the first derivative of this and equate to 0, whatever the solution is going to give us the minimum because of the shape of this function. Right? In part 2, we will take the derivative of this and then set that to 0, which is c times lambda over 2 times t plus k over t. Okay. And from here you get c times lambda over 2, and from here you get k over just t squared, right? And when you take this to the left, we have that. And from here, what do we learn? T squared goes to the right. You have 2k divided by c over lambda, and then we have to take the square root. Okay. That minimizes the dispatch cost, total waiting and dispatch cost. And this is the ideal, optimal dispatch cycle length. Okay. Any questions? Huh? All right. Okay. So this kind of considerations are important. If the costs depend dynamically on the number of customers already in the system, right? You can argue like that to find the total cost during any given time period. Okay. I have another problem from your textbook. And this informs us about a very important property of Poisson processes, which we will be using in other exercises extensively. Now this is problem 1.2 on page 276. Okay? Okay. And here is the question. Suppose that minor defects are distributed over the length of a cable as a Poisson process with rate lambda. So you have a cable, it may have been broken from time to time, if it is something actually subject to some environmental effects outside, right? It could be an electrical wire going from one place to another, right? It wears out eventually, and according to this question, statistically they concluded that the minor defects on a given piece of wire can be modeled by a Poisson process. Okay? And there are two types of defects. There are minor defects and there are major defects. Okay? Now, minor defects are distributed over the length of a cable as a Poisson process with rate alpha. And independently of the minor defects, major defects are distributed over the same cable according to also a Poisson process, but with a different rate beta. Okay? And now we are interested in the total number of defects, minor or major. Okay? And the question is that this new process, which counts the total number of defects, still a Poisson process? If it is Poisson process, what is its rate or intensity? Right? So if the answer for the first question is no, then we don't have anything to worry. So we have to first think and decide whether, if you count and sum all the number of defects, minor or major, do you still get a Poisson process? What do you think? It is yes? They are independent. But how can you convince others? So independence is one thing that you have to use in an argument that eventually convince us that it is Poisson. So obviously we have to check those two defining properties of a Poisson process. Right? If you want to verify, if you want to check whether some process is Poisson or not, we have to check two things. Does that process have independent increments? Does each increment of process over any given interval have a Poisson distribution? We have to check these two things. Now we already know that the two processes that we sum, right? The two processes that we sum together are Poisson, therefore they both have independent increments, and the increments over any given interval have Poisson distribution for each one of them. If we sum them, then the question is, if we sum them together, then do these two properties survive, right? Do we still have these two properties? Do they prevail and still remain valid for the process that we obtained by summing the other two? Okay? So we have to check that. So let's do that. Let's see how we can do that. So I am first going to define two processes, and in the meantime I am also summarizing the question. Let's denote by Y the number of minor defects. Okay? Minor defects on the cable, right, over the length T, or in the first T unit of the measurement that you use to measure the length, right? And let's use Z to count the major defects on the cable over the same segment of length T. Okay? And we are told now that Y is right? A Poisson process. So let me use PP to refer to that, with rate alpha, right? Okay. And Z is also a Poisson process, but possibly with a different rate beta. Okay. And we are also told that these two processes are independent of each other. Okay. So these are given. But we are also interested in the total number of defects, okay, on the same segment, right, of the cable. So this is the total number of defects, right, on the cable over a segment of length t. Now we know that this is given by the sum of y till length t and z till length t, right? So we sum these two things, two random variables, to find the number of defects over in any segment of length t. Okay, the first question is x, right, which is, of course, a continuous time process, if you just gather all these random variables over different t's together, a Poisson process. Okay, so that's the first part. We have the second part only if your answer for the first part is yes. Okay? If yes, then we will want to know what the intensity of this new process is. Okay? If yes, what is the intensity process of x? Because we need to know the intensity in order to be able to calculate mean, variance, anything that you think is important. Okay? Okay. If you look at the first part, as I said, to verify that x is a Poisson process, we should check if it has independent increments. Right? X is Poisson, right? If, okay, so two properties. The first one is x has independent increments. And meaning, maybe I should just write it because I don't know how much space I need to fill in there, right? Namely, we should verify what? For every integer n, 2 or more, and for every real number, for every n real numbers, t1, t2 up to tn, we have to verify that the change in the process, or the increment in the process from time 0 to time t1, from time t1 to time t2, and from time tn minus 1 to tn are independent. Okay. Okay. And if this turn out to be true, we also have to check that for every S and T, the distribution of the increment of this process from from S to T has Poisson distribution. With an appropriate mean. If it indeed turns out to have a Poisson distribution, then we have to also identify its mean, and that mean is going to give us the intensity, in fact, in the second part. Now we can quickly argue that they are independent, in fact, here. Why are they? Now, first of all, the increment of process x over this interval is the sum of the increments of processes y and z, right? Because x is itself the sum of two processes, right? Plug here t2, and then plug then t1, for example, subtract from each other, then you get what? Increment over the same interval for the process y plus the increment of the increment over the same interval of process z. Namely, this is yt1 minus yt0 plus zt1 minus zt0, right? And this is yt2 minus yt1, right? Change in y in over the same interval plus change in process z over the same interval, right? And finally, here you have the change in the process y over the last interval that you picked before, plus the increment in process z over the last interval from tn minus 1 to tn, right? Now, when you write all these things, then first, since y is itself a Poisson process, all these increments are independent of each other. Am I right? They are independent, right? And since z is itself a Poisson process, all of its increments are independent of each other, right? They are independent. And increments of y and increments of z, process z, are independent of each other because processes y and z are independent, right? So all random variables that I circled here are independent of each other. And you get these random variables by summing them up. Therefore, right, each one of them consists of random variables which are independent of each other. Therefore, they are independent. Okay? So increments are independent. For the increments of new process x are independent. Right? On the other hand, if you just use the same decomposition, you know the increment of process x over interval from s to t is the sum of increment of process y over the same interval from s to t, and increment of process z over the same interval from s to t, right? Now here we need to either remember or again remind ourselves that if you have two random variables, Poisson distributed random variables, right? So we know that since y and z are Poisson distributed, both of them are Poisson distributed, and they are independent of each other. So let me write it like the independent Poisson random variables. And there is a result that says that if you have two independent Poisson random variables, and if you sum them up, the new random variable is also going to have Poisson distribution, whose mean is going to be, of course, the sum of the means of other random variables. Therefore, we also know the mean of the new Poisson distribution. So I'll just go over this derivation one more time after we give a break. We are already late to give a break. Okay, let's give 10-minute break. Okay.